So the last speaker of the first day is Professor Valentino Tosatti from McGill University. The title of his first talk is Introduction to the Kähler-Ricci Flow, Part 1. Please, Professor Tosatti.
Thank you very much. Thank you for the introduction. And of course, thank you to the organizers for the kind invitation. I'll try to make the best out of this virtual situation. And so these three lectures will be about the Kähler-Ricci flow. Maybe they can go to the next slide. The Kähler-Ricci flow is, as you may imagine, is a version of the Ricci flow. So it's going to be an evolution equation for a matrix on a manifold. And as the name suggests, the manifold and the matrix are going to be Kähler. I will explain what that means. These are certain types of metrics on complex manifolds. So it's going to be an evolution equation for a Kähler matrix on Kähler manifolds. And we will try to see, first of all, the basics. Okay, so there will be today an introductory, kind of brief introduction about complex and Kähler manifolds, and if you want, the definition of the Kähler-Ricci flow, and then some motivation. And then we will see there's a short-time existence result, namely that starting at any initial metric, one can always run this flow. This was originally due to Richard Hamilton in the 80s. And we will also characterize and in many cases compute the maximal existence time of the flow. So for how long the solution exists. Then we will, in the next two lectures, we will get to the main part, if you want, which is where the current research is happening, namely, which is to try to understand the behavior of the flow when you reach the end of its existence. So there are basically two cases that we will discuss, right? One is when the flow exists only for finite time. So you develop a singularity in finite time, and we will try to have some basic understanding for what happens in these cases. And then the other case is when there is no singularity in finite time, so the flow exists for all positive time, and we will then try to understand the asymptotic behavior when time goes to infinity. I gave some lectures on this topic a few years ago in Pisa, actually, and I wrote some lecture notes back then, which you can find, for example, on the archive here. These lecture notes I will follow quite closely, at least in the first two lectures. So if you're looking for more details for some things that I say, the chances are that you will find the details actually in my lecture notes. So it's a good place to look at. The last lecture about infinite time, there will be some new developments that have happened since these lecture notes, but in any case, we first need to get there. And there are also two other very useful lecture notes on the topic. One by Ben Weinkoff. This one is somewhat more basic, so it's a good introduction if you're a really beginner in the topic. Here also on the archive. And then another set of lecture notes by Jan Song and Ben Weinkoff, which are longer and are somewhere in between level of difficulty, in between the ones of Ben and the ones by myself. So there are also many other places and books about Ricci flow in general, but these are more tailored to the Kähler case. Okay, so without further ado, let's start. So I'm sorry if the exposition at the beginning will be a little bit quick about the basics. So about complex manifolds, I'll try to at least say things clearly, but I won't be able to prove everything in the basics for sure. The basics of complex manifolds, there are many different places you can look at. In particular, I like the book by Daniel Huybrechts on complex geometry. That's a good place to find more details about the basics. Right, so I already said that the Kähler-Ricci flow is the evolution equation for metrics on a class of geometric spaces. So these are Kähler manifolds that we will see. And my manifolds are always, in fact, compact. So the case of non-compact manifolds certainly makes sense and can be studied. It's in general harder and doesn't have the relations with the algebraic geometry that we will try to discuss. So I will assume compactness and no boundary. So R manifolds are always closed manifolds, and they will always be connected, so that nothing is disconnected. So R manifolds are going to be complex. I will usually denote it by X, and N here will be the complex dimension. So X is going to be a complex manifold. So that's, as usual, a manifold covered by an atlas with charts. And now the charts, instead of being in Rn, like a smooth real manifold, they are charts in Cn, which certainly you can view as R2n if you want. But the key point is that the transition from one chart to the other are assumed to be complex analytic. So I will just call this holomorphic. So the domains and the codomain of these chart transitions are by definition open subsets in Cn. So these are holomorphic maps from an open subset in Cn to Cn. So that's just the usual generalization of the usual notion of holomorphicity in one complex variable. You just, if you want to assume that these maps are smooth and holomorphic separately in each variable. And so these manifolds are obtained by gluing pieces that are Euclidean, Cn, and the gluing maps are holomorphic. So the chart maps here, phi alpha, will disappear completely. So I will never write them again. And I will therefore identify U alpha here, which also disappears with its image, which is an open subset in Cn, right? So it has coordinates that I will always denote as Z1 to Zn. So with total abuse of notation, Z1 to Zn will be local coordinates, complex coordinates on X in some open set that I will not give it an explicit name. Okay, I will work in charts a lot. What are some simple examples of complex manifolds? So the simplest ones are when n is equal to 1. That's one complex variable. So these are obtained by gluing open sets in C. These are known as Riemann surfaces. Of course, I'm assuming compact. So here are some pictures of some compact Riemann surfaces of genus 0, 1, and 2. Other simple examples are tori. That's when you take Cn modulo a lattice lambda, which is isomorphic to Z to the 2n, which acts by translations. These are, of course, holomorphic maps. The quotient can be shown to be a compact complex manifold. It's diffeomorphic to the real torus of real dimension 2n. And projective space will play an important role in the lectures. That's the space of complex lines in affine space of dimension 1 more, so Cn plus 1, lines through the origin. So that's non-zero points modulo scaling. So this is C star acting by scaling. And this is a compact complex manifold of dimension n. And CP1 in particular is easily seen to be diffeomorphic to the sphere S2, this Riemann sphere here. There's a vast category of examples of complex manifolds, which are known as the smooth projective varieties over the complex numbers. This is where you take CPN, the large N, and take finally many polynomials, which are assumed to be homogeneous in big N plus 1 variables. So when you have a homogeneous polynomial in big N plus 1 variable, you can look at the zero locus of this polynomial in Pn. That's well defined. And then you can look at the common zero locus. So this gives you a subset of Pn. And you assume that the polynomials are somehow generic enough that the zero locus is actually a manifold. This is translating a condition on the first derivatives of these polynomials that is easy to check. And then this zero locus can be shown to be a complex manifold. For example, here is one of the simplest polynomials in 3 variables. So the zero locus will be inside CP2, and this is Z0 to the D plus Z1 to the D plus Z2 to the D, so one polynomial equal to 0. This zero locus is non-empty because we are looking at the complex solutions, and they give you some Riemann surfaces. Okay, so sorry, some slides are a bit dense with writing. Some basic calculus on complex manifolds. So let's work in coordinates, although one can make this construction global, but I just don't have time to go through different viewpoints. So I will work in some coordinate chart. And if I take the coordinate Zj, I can usually, as usual, write it as real plus imaginary, I imaginary. I can call this xj and yj. So if I take them together, they are local real coordinates. This is just viewing Cn as R to n. So these are the coordinates for the manifold as a smooth manifold. And imitating the situation in one complex variable, one can define so-called Wirtinger derivatives, d by dzj and d by dz bar j. So since I'm going to use this all the time, I use also this shorthand, partial j and partial bar j. That's a very quick shorthand. And you just define these with this hopefully familiar formula from, again, one complex variable using the real coordinates. So you see, you can think of them as derivations or vector fields. They are linear combination of this standard real vector fields, but the coefficients, some of them are complex. Like here, there's an I. So what it means in more globally, these are local smooth sections of the complexification of the tangent bundle. So the tangent bundle tensor with C. And I can define T10 locally if you want to be the span of the DZJs, and T01 to be the span of the DZJ bars. And these actually define two subbundles of the complexification, and together they give a direct sum decomposition. So 1, 0 vectors will be linear combinations of the DZJs, 0, 1 vectors of DZ bar Js with complex coefficients. And this splitting can be dualized. So for the dual, these are just a complex one forms, you get the splitting into the dual, and you define the dual of 1, 0 vector fields to be 1, 0 forms. I will denote them with this lambda notation, and the dual of 0, 1 will be 0, 1 forms. And you can again write a local basis of these smooth sections of these bundles of forms. I claim by simple computation, the dual basis of the DZJs, j from 1 to n, the dual basis is given, sorry, d by dzj, the dual basis is given by this dzj, which is just defined to be this one form, dxj plus I dyj. Again, it's a one form with complex coefficients. So this is a dual basis of this, and their conjugate formally dz bar j is a dual basis of these ones. So these give you a basis of 1, 0 forms and 0, 1 forms. And then one can define PQ forms for any P and Q between 0 and n by taking P wedge P copies of disease and wedge Q copies of DZ bars. This is the intrinsic formula. And then, but linear algebra, complex K forms then split as a direct sum of PQ forms when P and Q are between 0 and n, and their sum is equal to K. So this is, if you want, a refinement of the theory of differential forms that you have on complex manifolds. And the exterior derivative, so if I have alpha, a PQ form, locally in these charts, it's given by some smooth function alpha with a bunch of indices, many indices, times this basis elements, right? P of the disease and Q of the DZ bars. I can use multi-indices just for this slide. Capital I, capital J are the multi-indices. And then with this more compact notation, the exterior derivative, the alpha, this is given by the familiar formula in the real, using the real coordinates, x and y's, right? So this first equality is just the familiar formula from smooth manifolds. But then if you compute, you do a one-line computation, this d function dxk times dxk, when you sum, is the same as doing, plus the dy one. You will get the same as if you do dzk plus dz bar k. So this simple computation is the key to a lot of things. So you'll see that the exterior derivative of alpha can be expressed in this way using the complex coordinates and their conjugates, sum of two pieces. And I just define the first piece as del alpha, the second piece as del bar alpha. And I have thus proved that the exterior derivative is equal to del plus del bar. And since this map, del increases the pi degree PQ by 1, 0, del bar increases the pi degree by 0, 1, as you can see. So from this, it follows that since d squared is 0, it follows that del square is 0, del bar square is 0, and del bar anti-commute. Okay, so now some geometry. So the geometry is done with metrics, at least for me. So metrics on a complex manifold should be Hermitian because the tangent spaces are complex vector spaces. So this is the analog of a Riemannian manifold for a complex manifold. So this is just a Hermitian inner product on this bundle of 1-0 vectors, G. So it's sesquilinear and positive definite. And of course, it's very smoothly from point to point. And if I use local coordinates, I take these DZs and DZ bar local vector fields. I can evaluate the metric on these vector fields. I obtain local functions, G, J, K bar, local complex valued functions. Put them together, I obtain at each point a matrix, G, J, K bar, which is n by n and Hermitian. This is the Hermitian property, and positive definite. And when you change chart, it transforms in the way that you imagine. So the Hermitian metric G essentially is the same as this data GJK bar together with the transformation from one chart to the other. And I can compute if I have two 1-0 vector fields V and W. In these charts, I can write them in terms of the basis with these component functions. Then the Hermitian metric evaluated on V and W bar is just given by this GJK bar, VJWK bar. I will also use this bracket notation where I don't put the bar on the W then. And when you have a Hermitian in a product on 1-0 vectors, you obtain a Hermitian in a product on all the other associated bundles. For example, on the 0-1 by complex conjugation, on the dual bundle of 0-1 forms, the inner product is actually given by the inverse matrix. So if you compute in local coordinates, this positive definite matrix at each point, take the inverse matrix, and that's the entries of the inverse matrix, and that's the inner product on the dual. For example, we can compute what is the pointwise length of the Hermitian metric itself, viewed as a section of a T10 dual tensor T01 dual. So what's the length with respect to itself? Well, squared, that's the G. This one here is the conjugate because I use the Hermitian property, and these are the inner product on T10 and T10 dual and T01 dual. And then this is a matrix times the inverse, so you have a lot of cancellations and you just get n. So the length is actually the square root of n constant, which may look a little bit strange, but that's the normalization. And when you have a Hermitian metric, you can also obtain a volume form that I will usually call the DVG by taking the determinant of the Hermitian metric times this, you can say, standard Euclidean volume form. This is the up to a constant is the Euclidean volume form in Cn, the usual one, Lebesgue measure, if you wish. So if you're familiar with Riemannian geometry, in Riemannian geometry, you have a similar formula with the square root of determinant. Where did the square root go? Well, that's because the square root is still there if you view a Hermitian matrix n by n as a symmetric 2n by 2n real matrix. So if you do that identification, then you will get a square and the square root cancels. So it's really the same in a sense as what you have in Riemannian geometry. And so this is a globally defined top form, volume form, and strictly positive. And we can put it in the last line, but if you integrate this DVG, then you get what we will call the volume of X using the metric G, which is strictly positive, as long as X is not a point. You also can define a two form that we will use all the time called omega by taking the metric tensor and multiplying by this DZJ wedge DZ bar K. And for normalization, I also multiply by the imaginary unit. So this, you can easily check, is a globally defined 1-1 form on X. And it's also real in the sense that if I conjugate it, it's the same as itself. This is why I put the I. If you don't put the I, it would be a purely imaginary form. And this real 1-1 form has the property that the coefficients here are positive definite. That's the Hermitian product. And that property I shall write as omega strictly positive. So conversely, if I have a real 1-1 form, I can always write it in this form with some coefficients which are Hermitian, and then I will write positive if these coefficients are positive definite. And if you do that, then a simple computation, just linear algebra, shows you that the dVg is actually equal to the wedge product of omega with itself, n times, which is the maximum, divided by n factorial. So you have a simple expression for the volume element using this omega. So Kähler metrics are then Hermitian metrics on a complex manifold such that omega is closed. So the exterior derivative of omega is 0. That's the key definition for this course. If you write it down in local coordinates, again, I don't do the computation here, sorry, but it's very easy. You will see that this closeness condition actually is equivalent to this commutation of these partial derivatives. So in each local holomorphic chart, if I take g, j, k bar, and I take partial I, then it's the same as if I took partial j of g, I, k bar. And if you take conjugation, this is equivalent to the one when you take bar derivative. So if you took I bar, you would commute it with k bar. So the Kähler condition is really, if you want, a system of first order linear partial differential equations on the coefficient g, j, k bar. So it's not a trivial condition, it's indeed a PDE, a system of PDEs. This condition was introduced by Erich Kähler, was also somehow studied separately by other people earlier, but he was really the one who gave the right motivation and the outlook on the whole theory. As I said, this condition is non-trivial. However, many natural manifolds that we will counter satisfy this. And as the title of the lectures has the word Kähler, from now on, all complex manifolds will be assumed to admit Kähler metrics. So what are examples? So the Riemann surfaces are Kähler because omega, you fix any Hermitian metric on your Riemann surface. G, you look at the one form omega, that's a 2 form. So d omega is a 3 form, but the Riemann surface is only 2 real dimensions. And so the 3 form must be 0 just by degree reasons. And so all Riemann surfaces are Kähler. Complex tori, they defined earlier, are Kähler because I can take a Euclidean metric on Cn. You have many Euclidean metrics, just fix, these are constant coefficient metrics on Cn. And if they're constant coefficient, they're invariant by translation. So they descend to the torus. And because they're constant coefficients, these partial derivatives are 0. So they are Kähler. So tori are Kähler. Projective space is also Kähler. One can write down explicitly a Kähler metric called Fubini studi. Here is the formula before you take the quotient. So on Cn plus 1 minus 0, it's up to this factor of 2 pi. It's IDD bar log of the norm square in n plus 1 variables. So it takes a little computation to check that this descends to Pn and that it is positive definite. However, you can see that it's certainly going to be closed because at least upstairs is even exact, dd bar exact. So furthermore, one can easily see that the Kähler property is inherited by restriction to complex submanifolds. So if you have a complex submanifold of a Kähler manifold, the restricted metric is still Kähler. In particular, smooth projective varieties are all Kähler. You can restrict, for example, Fubini studi. And a nice property of Kähler metrics, which is going to be useful later for computations, is that you have local holomorphic normal coordinates. And even more, if you have a Kähler manifold, x omega, and you also have another real one form alpha, it doesn't have to be closed. And given any point, you can find some local holomorphic coordinates centered at this point, such that in these holomorphic coordinates at the center, the metric G is the identity, like this Kronecker symbol. The first derivatives all vanish. And furthermore, this alpha, which is in local coordinates is just a Hermitian matrix, is diagonalized. So this diagonal and the eigenvalues are necessarily real numbers at the center of the chart. So this can all be achieved. You can find the proof, I think, in the lecture notes of Ben Weinkopf, I believe, also in standard books. But usually the standard books do not have the additional alpha here. They only have discussed the G. So not the simultaneous diagonalization of 2. However, very importantly, if you assume, even if you assume that alpha is positive definite, so if you assume that alpha is another Kähler metric, you cannot achieve that the first derivatives of alpha are also 0 at the same time as the ones of G. So you cannot in general have normal coordinates that are normal for 2 different Kähler metrics. What you can achieve is that they're normal for one and you diagonalize another one just at the center. So the Kähler property gives us some extremely useful information, which by definition, if you want, lives in cohomology. So the de Rham cohomology H2 is the usual space of closed real 2 forms modulo exact real 2 forms. And if you have a Kähler metric G, the Kähler form that I will also by abuse of notation call the Kähler metric omega is closed, right? It's a closed real 2 form. So the Kähler form will define a cohomology class in H2. And in fact, it's not only closed real 2 form, but it's also a real 1-1 form. So it actually defines a cohomology class in a subspace that I will call H11 XR. This is a subspace of de Rham cohomology classes that contain a representative, which is a closed real 1-1 form. So by definition, if I take a Kähler metric G and compute the Kähler form omega, it defines a class with a square bracket, which lies in this H11. So this H11 is a linear subspace of H2. The manifold is compact, so H2 is finite dimensional. So H11 is a finite dimensional vector space over R. And if I look at all the possible classes of all Kähler metrics on X, I can take if you want, all of these together and define this set CX, which is just a subset of H11. And this CX is called the Kähler cone of the manifold. And it's not hard to see that it's an open and convex cone in this vector space. You can see the proof that the only part that is not kind of obvious is the openness. You can find the proof in my lecture notes for the openness in the first chapter. This cone here, there's a schematic picture. I stole this famously from lecture notes of Demailly. So thank you, Jean-Pierre. so this is a schematic picture of what this cone might look like. It may have some kind of it's open. So the boundary, that is what you kind of see here, is not part of the cone. And the boundary may have some complicated geometry, may have some polyhedral faces, and then maybe some round part. So the geometry of this cone, or the boundary of this cone in general, is highly non-trivial. We will study this cone in more detail in the next lecture. But the point is, you can think of this cone as some shadow of the space of Kähler metrics on X, or a very naive parameter space of Kähler metrics, simply looking inside this cohomology space, H11. So it's some finite dimensional shadow of this big blob, which is the space of all Kähler metrics on the manifold X. And an important theorem of Kodaira states that if you have 2 closed real 1-1 forms, alpha and beta, and you assume that they're de Rham cohomologous, so that their difference is exact, is d gamma for some real 1 form gamma, then the difference is not only exact, but it's what's called the dd bar exact. So you can write alpha minus beta as I del bar phi, where phi is a smooth real valued function, and phi is actually unique up to addition of a constant. That's important. And if you want, using local coordinates, that means that this Hermitian matrix alpha jk bar is equal to the other Hermitian matrix beta jk bar plus this Hessian d square phi dzj dz bar k. So this is really the complex Hessian of a function phi. So because of this remark, one can view H11 as alternatively as the space of closed real 1-1 forms modulo IDD bar exact ones. Okay, 2 more slides of basics. Sorry, I will go through this a bit quickly. I will actually won't use too much of these explicit formulas, but something that will be important is going to be the trace. So if I have a Kähler metric G, I will actually write omega from now on, and alpha another real 1-1 form. I can define the trace of alpha with respect to omega simply by taking the inverse of G and tracing it with alpha in coordinates. This is, of course, independent of the coordinates you pick. So it's a smooth function on X, and it can also be defined by this identity. So if I take alpha, I wedge it with omega to the wedge power n minus 1, and I multiply by n. This is a top form, and this top form certainly must be proportional to the volume form, omega to the n, and the proportionality factor is exactly this trace. So you can check this by yourself, for example, using coordinates that make omega the identity and alpha diagonal at one point, then this becomes kind of clear. Right, so this trace is important, and in special cases when you trace IDD bar of a function, that's the trace of the complex Hessian. It's just this formula here, and this is called the Laplacian, or a complex Laplacian of f. And it's not quite the same as the usual Laplace operator. For example, in Euclidean space, Cn with the Euclidean metric, this is 1/4 of the usual Laplace operator, but that's not important. So I will just call this the Laplacian. You have, for a Kähler metric, the usual geometric objects. You can define a connection on T10 called the Chern connection, which is, if you want, the analog of the Levi-Civita connection, by defining its Christoffel symbols, gamma, ijk, simply by this much simpler formula than the one for the Levi-Civita connection. You take just in local holomorphic coordinates one derivative of G contracted with G inverse. And these, from the Kähler property, you can see is symmetric in I and J. So they satisfy this torsion-free property. And these Christoffel symbols, they're not the components of a tensor, but you can use them to define covariant derivatives of tensors. For example, again, I always work in coordinates with indices. I'm sorry if you dislike this. So if you have V, which is Vi are the components of a 1,0 vector field, you can define nabla V, component I in the direction d by dz to be the partial derivative plus the Christoffel times V. And on the other hand, in the d by dz bar direction, you do not put the Christoffels. The Christoffels are 0, so you just take the partial. And similarly, you can obtain induced connections on all the other tensor bundles. In particular, a simple computation will show you that if you take G, or equivalently omega, if you want, view it as a tensor, then it's annihilated by nabla. You can check this very easily. So this is the metric compatibility connection. So the Chern connection is the connection on T10, complex connection really, which is symmetric and torsion. So, I mean, torsion-free and metric compatible, just like the Levi-Civita connection. And the formulas, however, are simpler because we're working with Kähler manifolds. In particular, the Riemann tensor is also simpler. It's just one derivative of the Christoffel instead of being many terms, like in the Riemannian setting. And usually we will lower one index. So it looks like I, J bar, K, L bar. It's, you see, one derivative of the Christoffel, which was itself one derivative of the metric. So morally, it's two derivatives of the metric. It satisfies this real property. If you conjugate it, it's basically equal to itself. You just need to switch the barred and unbarred indices. And then it satisfies the first Bianchi identities, which are, again, much easier than for Riemannian metrics. It's symmetric. You can switch around the indices of the same type without any impunity. So with impunity. And it satisfies the second Bianchi identity, that if you take a nabla, you can switch the index. If you take an unbarred nabla, you can switch it with I or with K. And if you took a bar derivative, you could switch it with J or with L. And again, as in the Riemannian world, the Riemann curvature tensor arises when you commute second order covariant derivatives, but only when you commute one with bar and one without bar. So commuting bar and bar does not incur a curvature, and similarly commuting unbarred and unbarred does not incur curvature. All right, so the important object for us is the Ricci curvature, which is the trace of the Riemann. So you just trace two indices, R, J, K bar. it's from the real property of the Riemann, you can see that it's Hermitian. These are really the components of a tensor of the same type as G, which is Hermitian. And it has this very nice formula in local coordinates that you can prove directly from the definitions here, that it's minus dzj, dz bar k, oops, of log determinant of the metric. This very elegant formula is the key to a lot of things in complex geometry. If you trace it once more, you get the scalar curvature that we will call R without any, this is just a smooth function. So again, there's some global aspects from the Kähler property, namely, now that you have this tensor RJK, it's very natural to turn it into a real one-one form, exactly like we did with the Hermitian metric G. So you do that, you can define Ricci of omega, which is the real one-one form whose coefficients are the Ricci curvature. So locally, by that beautiful formula, it's just minus IDD bar log of the determinant. This only makes sense locally because the determinant of G is only a locally defined function. But when you take minus IDD bar, this becomes a global form. So being locally DD bar exact, certainly this form is closed. So it's a closed real one-one form, exactly like omega. And furthermore, if you take the difference of two Ricci forms, then you have the same formula here. I write the determinant, the ratio of determinants is the same as the ratio of the volume forms. And now this function here, log ratio of the volume forms of two metrics, this is a global smooth function. It isn't local anymore because the ratio of the two determinants becomes global. So the difference of two Ricci forms is not only closed, but it's actually DD bar of something. In particular, it's exact. So the conclusion of this computation, which was already in Kähler's paper, is that if I take the cohomology class of the Ricci form, for normalization purposes, I divide by 2 pi, then this cohomology class is independent of the choice of omega. So if I fix a Kähler metric and I compute the Ricci curvature form and I divide by 2 pi, the cohomology class is the same for independent of omega. And this class we shall denote the Firtian class of X, C1 of X. So it's a class in H11. So how do you compute it? Well, certainly you can compute this Firtian class if you can compute the Ricci curvature. So for example, if you take a torus and take a Euclidean metric on the torus, omega E, then as I said, it's constant coefficients. So there is no curvature whatsoever. In particular, the Ricci curvature is 0. And so the Firtian class is also 0. So that's for, I didn't write it, but that's obvious for tori. Fubini studi, one can do a computation and see that the Ricci curvature form of Fubini studi is a multiple of itself, and the multiple factor is n+1. So in particular, if you want the Firtian class of the projective space is given by n+1 times the cohomology class of Fubini studi divided by 2 pi. There's another Kähler metric that I didn't discuss earlier, the Poincaré metric on the ball. So this is the unit ball in Cn, vectors with length less than 1. One can define explicitly a Kähler metric, which is minus IDD bar log of 1 minus mod c square. It's some kind of analog of Fubini studi with a sign change. And the Ricci curvature is minus n+1 times itself. And the ball isn't compact, but there are, one can often find discrete groups that act on the ball by isometries of the Poincaré metric, and the quotients will be compact, often complex manifolds where the Poincaré metric descends. So the standard examples are Riemann surfaces of genus 2 and higher, which are quotients of the B1, which is just a disk in C. Okay, and then for hypersurfaces, smooth hypersurfaces in projective space, let's say in Pn+1, so X is n-dimensional. If it's the zero locus of one polynomial of degree D, then a computation gives you that the Firtian class is given by this multiple, n+2 minus D, times the restriction of Fubini studi from Pn+1 divided by 2 pi. So you can see that the it's according to whether D is small or large, this will behave differently because this is the restriction of a Kähler class, but this coefficient has different signs according to the values of D. Okay, so finally we get to the Ricci flow. We have all the basic ingredients. So we'll have, as I said, a compact Kähler manifold Xn. Omega 0 will be the initial metric. So it's going to be a Kähler metric on X. And we will define, if I have a smooth family of Kähler metrics, omega t on X, so they vary smoothly in T, and T varies in some interval, 0 capital T. So we will say that this family of Kähler metrics solves the Kähler-Ricci flow if stated, say, in terms of the corresponding forms. The time derivative of omega of t is equal to minus the Ricci form of omega of t. And the initial omega of 0 is our omega 0 here. So this is the same as Hamilton's Ricci flow up to a factor of 2. If you know Ricci flow, usually it's in the Riemannian world, it's dGdt, it's minus 2 Ricci. So this factor of 2 just corresponds to speeding up or slowing down the time by 2. So it's not important at all. And it's much nicer in the Kähler world to not put the factor of 2. So it's defined without the 2. And so this is just a definition and would be useless if you don't know that this exists, that such Kähler-Ricci flows exist. But luckily, they exist in great abundance, thanks to this theorem of Hamilton, which of course is much more general since it applies to Riemannian manifold. But let me just state it for Kähler manifolds. So if you have a compact Kähler manifold with the omega 0, the initial metric, you can always find a unique solution, which is smooth, of the Kähler-Ricci flow, defined on some maximal time interval 0 capital T, where capital T is a strictly positive. So you always have some solution for some time, and it may be even infinity sometimes. And maximal means maximal on the right. I'm not trying to solve backwards. I do not look behind 0. So maximal forward. There is no further larger T prime for which the flow exists. Here is a cheating picture of what this flow is supposed to do. Naively, very naively, you see in the places where the Ricci curvature is positive, the metric is shrinking, right? Because the metric is minus Ricci. That would be in this picture, this tips of this dumbbell. And in the places where Ricci is negative, the metric is expanding. That would be inside this necks here. So the necks tend to expand, the dumbbells tend to shrink. And in this picture, you see some kind of a spheric thing at the end. Okay, so just one slide without formulas. So we will explore this flow in great detail in the remaining lectures. It will give us somehow a canonical way to deform and smooth out an initial manifold, which may have a very bumpy and rough shape, like this dumbbell here. And it tends to make the metrics more round in some sense. What does that even mean? We will try to see. The fixed points, naively, the fixed points where the time derivative is 0 are metrics with the Ricci curvature equal to 0. But you can also look at fixed points modulo scaling. So those that are just scaled by the flow, and those that are scaled turn out to be, instead of just Ricci equal to 0, Ricci is proportional to the metric. And these are called Kähler-Einstein metrics. So Ricci is lambda omega and are one of the basic objects studied in Kähler geometry. So Kähler-Einstein metrics arise as fixed points, basically, of the flow. The Riemannian version of the Ricci flow for real 3 manifolds was, of course, famously used by Perelman, completing a program of Hamilton to prove the Poincaré conjecture and also the geometrization conjecture. So it's a great success story. It also arises in theoretical physics, in quantum field theory. I'm actually not qualified to talk about this at all, so don't ask me. So what I want to discuss, at least the rest of the lecture, is this short-time existence, and hopefully do a little bit of the maximal existence time. So here starts the actual meat of the class. So the first claim is that the Kähler-Ricci flow equation, which maybe I displayed one more time here, can be actually equivalently written as a scalar PDE. So the claim is that if you have some family of metrics varying smoothly in T, on some time interval, then they solve the Kähler-Ricci flow on this time interval if and only if there is a family of smooth functions phi t, depending on t, such that your metrics omega t are actually equal to omega 0 minus t Ricci of omega 0 plus dd bar of phi t. So these metrics can be obtained essentially by two derivatives of phi up to this background initial data. And phi t solves the following equations. First of all, this should be positive definite, right? Because it's a Kähler metric. Secondly, the initial data is phi at time 0 is 0. And lastly, the important one, the time evolution of phi, d phi dt, is given by log, the natural log of the ratio of the volume form of, this is just the volume form of omega t, divided by the volume form of omega 0. And this equation should hold on x for all time. So this equation we will discuss in the next slide. Let me first give you quickly the proof of this equivalence. So one direction is easier, namely assume that you have this and prove that omega so defined satisfies the Kähler-Ricci flow. That's very easy. You just compute d by dt of omega. You differentiate this equation here. So you just get minus Ricci, that's this derivative, plus dd bar of d phi dt, that's this derivative. For d phi dt, you substitute this equation. So you obtain that you have to do dd bar log of the ratio of the volume forms. But dd bar log of the ratio of the volume forms is, as I said earlier, the difference of the two Ricci curvatures. So this term here becomes plus Ricci omega 0 minus Ricci omega t. So those cancel, and you get exactly the Ricci flow equation. Okay, so one direction is easy. The other direction is also not hard, but slightly more confusing. So you assume that omega of t solve the Kähler-Ricci flow. Define phi t by this Riemann integral. So you integrate in time the log of the ratio of the volume forms of omega of s. This is the matrix that you have that solves the Kähler-Ricci flow. So by the fundamental theorem of calculus, the d phi dt is equal to this log of the ratio of the volume forms, and certainly phi of 0 is 0. However, we don't know the relation yet between omega of t and this dd bar phi t, right? So to find that, you then compute the time evolution of the difference between omega of t minus what you expect, omega 0 minus t Ricci omega 0 plus dd bar phi t. So take the d by dt of this, new compute. So d by dt of omega is minus Ricci. That's because omega satisfies the Kähler-Ricci flow. D by dt of this is the same computation I just did. You get plus Ricci because of this minus sign and because of this equation here. So you get 0. So the difference of these two does not depend on time, right? And if you compute at time equals to 0, omega of 0 is omega 0. Omega 0 here cancels. This term is 0, and phi at time 0 is the constant 0, so dd bar is 0. So you obtain that this difference starts 0 and doesn't change in time, and so this difference is 0, tout court. And so in particular, omega t must be equal to omega 0 minus t Ricci plus dd bar phi t, what you want. Now you can plug it into this equation, right? This trivial equation together with this gives you exactly this PT. So what did we gain by this trick? We gain a lot because this is now an equation for a scalar function phi rather than a PDE for a metric tensor omega. So in particular, we can, okay, probably I will stop after this. We will prove or sort of sketch the existence and uniqueness theorem of Hamilton, right? So as I just said, instead of working with the Ricci flow equation, I can work with this. This equation here looks pretty nasty because here you have the time evolution of phi. On the right-hand side, this differential operator of phi looks roughly like some fixed stuff, two derivatives of phi, and this nth power, as we discussed earlier, that's the same as determinant. So if you forget about this log, it involves the determinant of the complex Hessian of phi. That's a highly nonlinear quantity unless you're in one complex variable. And this is called the complex Monge-Ampère, when you have something involving determinant of the complex Hessian. And since there is a d-phi-dt on the left, this is falls in the category called parabolic complex Monge-Ampère equation that I think Vincent also discussed or will discuss. So in particular, we have a PDE, and we can compute the linearized operator, simply by taking this PDE here, applying the PDE to our phi t plus a perturbation, let's say tau times psi of t. Tau is a real number, and you take the d by d tau at tau equals to 0. For the left-hand side, clearly you just get d psi dt. And for the right-hand side, oh, sorry, there's a typo. This should be psi, not pi. For the right-hand side, when you differentiate, you get, because of the log, and you set tau equals to 0, on the bottom you have omega of t, and on the top you need to differentiate this, so you get n omega of t to the n minus 1 times dd bar of a psi. And now you recognize this as the trace from a few slides ago, is the trace of dd bar of psi. And so this is the Laplacian of psi with respect to omega of t. So you get this heat equation, time-dependent heat equation, d psi dt is equal to the Laplacian of psi t, but the Laplacian also depends on this family of metrics. In any case, the linearized operator has the form d psi dt equals an elliptic operator, the Laplacian. So this is called a strictly parabolic PDE, scalar parabolic PDE. So one can just quote, let's say with quotation marks, a standard theory and obtain a short time existence. So it's a little bit hard to find the standard theory on manifolds, but there are at least books, for example, Krylov and Lieberman, that discuss the standard theory in Euclidean space at least. And the uniqueness, that, as I said, probably the last thing we do, we can do by hand without appealing to any black box. So if you have two solutions for a short time, some time interval of the Kähler-Ricci flow, by the discussion on the previous slide, we can write them as omega 0 minus t Ricci plus dd bar of phi j, right? Omega j, j is 1 and 2. And we're trying to show that they're equal, right? There are two solutions with the same initial data. We're trying to show that they're equal. So let's take the difference of phi 2 minus phi 1, call it psi, and compute what's the evolution for psi. So d psi dt, if you take the two equations here, one for omega 1, one for omega 2, together they give you, because of the difference of the log is the log of the ratios, you get this right-hand side, and you can write omega 2 as omega 1 plus dd bar psi. That's the key trick. So you obtain this Monge-Ampère equation here for psi, and of course omega 1 plus dd bar psi, that's equal to omega 2, which is strictly positive, and psi at time 0 is 0, because phi 1 and phi 2 are both 0 at time 0. And we're trying to show that psi is identically 0. That would mean that phi 1 and phi 2 are equal, so omega 1 and omega 2 are equal. And this is application of the maximum principle. So let's do it slowly the first time, and then all the later times I will skip the simple details. So first you fix epsilon positive, and you take psi and subtract epsilon times t, call it psi epsilon. Let's see what's the equation. Oh, yes, there's another typo. Excellent. Sorry, I will fix the typos before I post the slides. So here there's supposed to be a minus epsilon, right? Because I have added this epsilon t. So you gain a minus epsilon. Here nothing changes because epsilon t is constant in space. And now look at apply the maximum principle. So fix a t prime strictly less than t, and look at this compact space-time, x times 0 capital T prime closed. This is compact, so psi epsilon achieves a maximum somewhere at some point xt. And let's assume first that t is strictly positive. Then from the second derivative test, the complex Hessian of psi epsilon at that point at xt is semi-negative definite because it's a maximum in space. And the time derivative is non-negative because, I mean, it would be actually 0 if t is strictly less than t prime. And if the maximum happens to be achieved at the endpoint t prime, then the derivative has to be going up. So it's bigger than or equal to 0. So on the other hand, if it was achieved at t equals to 0, you will get the reverse here, right? So anyway, they have the right signs. And on the other hand, since this is semi-negative, if you look at omega 1 plus dd bar of psi epsilon, is semi-negative, so it's less than or equal to omega 1. It's also strictly positive because it's equal to omega 2. So then you can pass to the determinant of this inequality, and you get the same inequality between determinants. But this is exactly this ratio here. So you get that at this point, the right-hand side is less than or equal than log of 1, which is 0. Right? And there was also a minus epsilon here. So you get that the deep epsilon dt on the one hand is non-negative, on the other hand is less than or equal than minus epsilon. And that's absurd. Conclusion, it was not possible to achieve the maximum at t strictly positive. So the maximum must be achieved at t equals to 0. But at t equals to 0, psi epsilon vanishes. So that means that the maximum on this space-time is less than or equal to 0. And then you can let epsilon go to 0, and you get to the maximum of psi. The psi is less than or equal to 0, and then you let t prime go to t, and you get the psi is less than or equal to 0 on your original x times open interval. And similarly, using the psi t plus epsilon t, you obtain the psi is bigger or equal to 0 on space-time, and therefore finally psi is identically 0. Okay, so this completes the proof of the uniqueness. So we have, I'm just going back, we have given, if you want, a sketch of the proof of this theorem here, right? So that you have a solution for a short time. Existence was essentially a black box, and actually you can find some more details in my notes, and uniqueness we proved. And once you have existence, by definition, you can take t to be maximal. So the fact that there exists a maximal one is just a tautology. Once you know, the non-tautology part is that the maximal existence time is strictly positive. Okay, so we will continue from here, I think tomorrow, right? I think this is a good place to stop here. So I'm happy to take any questions. Sorry if it was probably a bit fast-paced. Any questions or comments?
First of all, many thanks to Valentino for his beautiful talk. So are there comments, remarks, or questions?
I mean, yeah, it's not too much happened today, I have to admit. There was mostly basics, but we set up at least all the basic things that we would need. So if you want, the preview for the next one will be to find the formula for this maximal existence time. That certainly is not standard theory, and then compute it in as many examples as we can. So that would be the next step to find this maximal existence time.
Okay. So no questions. Okay, so we will start again tomorrow.